Hello, everyone. Today we are presenting our paper, Upper Limb Geometric MyoPassivity Map for Physical-Human-Robot Interaction. This paper was based on research conducted at New York University. Nowadays, applications based on physical-human-robot interaction, PHRI, have been widely seen. PHRI means humans are in direct contact with the robotic system to accomplish tasks. The application scenario include medicals, for example, exoskeleton rehabilitation and robotic surgery. And during the PHRI, there are two things that are critical and have to be guaranteed and optimized between the humans and the robots. One is the safety of the interaction, and the second is the transparency and the fidelity in the information transfer. For example, we want the force applied to the humans to be exactly the force generated by the robots. In order to guarantee those perspectives, there are some solutions and methods has been proposed and mentioned in the literature. For example, one popular structure is the time domain passivity approach, TDPA, which has two components, the passivity observer, PO, and the passivity controller, PC. The passivity observer will keep observing the system energy level, and based on that, the passivity controller will adaptively modulate the velocity and the force to guarantee the system is passive and thus stable. However, even though the system can stay stable after implementing this stabilizer, the cause is that the delivered force and velocity got modified and the system's transparency got degraded. In order to improve the transparency of the system, some researchers try to incorporate human biomechanics into the stabilizer design, which means that when they are designing the stabilizer architecture, the energy absorption capability of the humans, which is related to the excess of passivity, is taken into account. They use this amount of energy margin to absorb the energy that is supposed to be damped out by the stabilizer, resulting in less activation of the stabilizer and thus better systems transparency. However, even though we know the biomechanic energy margin is useful, there are two questions. How much energy can the human biomechanic observe, and does this number change under various situations? Therefore, in order to have a better understanding of the energy absorption capability of the human upper limb, we try to investigate how the interactive frequency and geometric direction affect the excess of passivity. And we also look into how the excess of passivity will change with muscle contraction detected by the EMG sensor.
As a basic overview, we discussed the definition of passivity and the output strictly passive condition from strong passivity theory. The total energy of an n-port system depends on the summation of the energy of each input-output pair. The energy is computed as the integral of the input times the output. For the system to be passive, the energy in the system must be positive, meaning that the system dissipates energy instead of generating energy. The output strictly passive condition defines an additional margin that encodes the extent to which a system is passive. The margin is encoded as the variable xi, and that can be considered as the excess passivity when positive. We have created an experimental setup to measure the excess passivity of the participants in our study. The participant is seated so their elbow makes a 90-degree angle when holding the handle of the robot indicated at the center location of the graphical user interface. EMG sensors are placed on the arms to measure the muscle co-contraction level of the forearm. These are processed into two bar graphs showing the percentage of muscle co-contraction compared to the maximum muscle co-contraction of the forearm. This is provided as visual feedback to the participant. At the same time, the robot perturbs the hand at set frequencies with no velocity profiles. The reactive force is measured and the excess of passivity is calculated. The experiment is conducted for 2 levels of muscle co-contraction, 8 geometric directions of perturbation, 10 seconds for each perturbation, and 2 interactive frequencies of perturbation. This results in 32 EOP values measured for each participant. 5 participants took part in the study, and the study was approved by the Institutional Review Board of NYU. The results of each participant is made into a concise map showing the EOP values in each direction. We call this map the geometric myopassivity or GMP map. The low-frequency maps are shown in blue and the high-frequency maps are shown in red. We generate the map for the relaxed and the stiff muscle co-contraction conditions. As can be seen, the low-frequency EOP value is higher than the high-frequency EOP values. This trend is observed for both the stiff and the relaxed muscle co-contraction conditions. Also, the EOP mass of the stiff muscle co-contraction condition are larger than the EOP mass of the relaxed muscle co-contraction condition. These trends are observed in all directions. To better visualize and understand the results, we perform statistical tests on the EOP value distributions. Figure A shows the median GMP map, which makes the trend from the previous slide even clearer. In Figure B, the EOP values are separated into 4 subgroups: high-frequency relaxed, high-frequency stiff, low frequency relaxed, and low frequency stiff. This figure shows that the EOP increases with muscle co-contraction and decreases with frequency. Figure C shows the EOP versus percent MVC plot for one participant. A trend line for the low frequency values and high frequency values are created. The slope of the trend lines for all participants are shown in figure D. This shows that as the interactive frequency increases, the slope decreases, thus showing that the influence of a higher muscle contraction is minimized as the interactive frequency increases. In conclusion, in the study, we investigated the natural damping ability of the human upper limb known as the axis of passivity. We have shown that the interactive frequency is a modulating factor on the biomechanical axis of passivity. Specifically, low-frequency interactions result in a higher EOP value than high-frequency interactions. In addition, the influence of muscle co-contraction decreases as the interactive frequency increases. Thank you for your time. This work was supported by the United States National Science Foundation.